Surviving the first year on Mars isn't about any single catastrophic threat. It's about whether your systems, your food, your power, and your mind can all hold together long enough to reach day 365. 1 year sounds manageable. A year is nothing. People do harder things in a year. But on Mars, that year is a clock counting down on 6 interlocking systems that all depend on each other, every single one of them degrading from the moment you land. The landing was clean, the habitat pressurized correctly. You run your first systems check. Oxygen production running, water processor running, solar panels reading 94% capacity. 94, not 100. Dust collected during descent. Already. You have 364 days before the next launch window back to Earth opens. You will not see another supply ship for at least 2 years. And somewhere between today and day 365, a dust storm is coming. You don't know when, you don't know how long it will last. That 6% power loss on day 1 is the first whisper of what will eventually become a roar. Your solar panels on Mars are like a smartphone screen that someone keeps smearing with dust and you can never wipe clean. Each Martian day, a thin layer settles. A week in, output drops a little more. A month in, your panels are producing noticeably less than they did on landing day. The dust doesn't announce itself. There's no alarm. The trend line just quietly bends downward while you're busy with everything else. And everything else is a lot. Every survival system you brought with you runs on that electricity. The machine that pulls breathable air out of the carbon dioxide atmosphere, which is the only atmosphere Mars has, runs on electricity. The heater runs on electricity. The water processor runs on electricity. The lights over your food crops run on electricity. Lose enough power and these systems don't fail one by one. They fail in sequence, each collapse triggering the next, like a row of dominoes where the last one is your oxygen supply. Here's the thing about the oxygen machine. NASA actually tested one on Mars. It's called MOXIE, and it flew on the Perseverance rover. It worked. On a good run, it produced enough breathable oxygen to keep one person alive for 10 minutes. 10 minutes. A crew of 6 needs a version of that technology producing roughly 50 kilograms of oxygen every single day. That's enough to breathe, plus extra for rocket fuel production when you eventually need to leave. The version that would actually keep a crew alive is roughly 700 times the size of the one that was tested. That larger version has never been built. It has never operated on Mars. You're arriving to install it from scratch, in a pressurized suit, on a surface where the temperature swings from warm enough to be comfortable at noon to cold enough to freeze the fuel in your backup generators by midnight, every single day without exception. That 90-degree daily swing isn't dramatic. It's grinding. Every seal in your equipment flexes with that temperature change. Every gasket compresses and expands. Every connection point works itself slightly looser with each cycle. You don't feel it happening. Your instruments might not catch it, but it's happening. Now, pause for a moment. Think about this problem directly. You have mass budget for exactly one of the following: a backup oxygen extractor in case the primary fails, or 6 extra months of food in case the mission runs longer than planned. The oxygen extractor has a 95% chance of surviving the full year without a backup. Which do you bring? Think about it before continuing. A 5% failure chance means roughly 1 in 20 missions loses its only oxygen source. The food gives you a certain benefit in a certain crisis. The backup extractor protects against a 5% chance of everyone dying immediately. Most people hearing this for the first time choose the food. The math says choose the backup extractor. A 5% chance that everyone suffocates within hours is not an acceptable risk to trade for extra calories. But every kilogram you bring costs mass budget that could be something else, and this is the impossible arithmetic that mission planners live with. There is no comfortable answer. Your food situation has its own quiet countdown running in parallel. The 9-month transit from Earth to Mars is not kind to packaged food. Nutritional content starts dropping from the moment the food is sealed. Vitamin levels fall, caloric density shifts. By the time you land, your food is already 9 months old. By month 8 on Mars, you're eating food that's been packaged for 17 months, which is approaching or past the point where the nutritional content has degraded measurably. The calories are still there, the vitamins are not reliably there. Growing your own food is the obvious solution, except the Martian soil is laced with a chemical called perchlorate, a naturally occurring contaminant that is toxic to humans in quantity and kills plants reliably. You cannot plant anything directly in Martian dirt. You need hydroponic systems, contained growing chambers, artificial lights, imported nutrients. Those systems need to be running within the first few months. They need electricity to run. The same electricity your dust-smeared panels are producing less of every week. Everything connects to everything else, and that connection is what makes the dust storm the real test. Dust storms on Mars aren't rare events. A storm big enough to cut solar power by 30 to 50% hits somewhere on Mars every single Martian year, which is about 1 year and 10 months of Earth time. A global storm, one that covers the entire planet simultaneously, happens roughly once every 5.5 Earth years. The 2018 global storm reduced surface sunlight to less than 1% of normal at its peak. Think about that. Not 50%, not 10%, 1%. That storm killed NASA's Opportunity rover, a machine that had survived 15 years on Mars, by starving it of power within weeks. Opportunity had no people inside depending on heat, oxygen production, or food-growing lights. It simply ran out of electricity and went silent. You would run out of all three. Day 90, a regional storm hits. Your solar power drops to 40% of normal, enough to run oxygen production and heating, but not enough to run both of those and keep the hydroponic lights on. The crop you've been growing for 3 months, the one you were counting on to supplement your food supply from month 7 onward, is on life support. You can save it by cutting power elsewhere, but cutting power elsewhere means something else degrades. Or you can sacrifice the crop and protect your core life support, accepting that months 7 through 12 will run entirely on packaged food that's already well past its best point. Think about what you would do. The storm might end in 3 weeks, or it might last 3 months. You have no way to know. The 2018 storm lasted 8 months. Opportunity waited for the sun to come back. The sun came back too late. By day 240, if you made it this far, the math has been running quietly in the background of every decision you've made. Your panels are producing less power than on day 1. Your food is older than it's ever been. Your equipment seals have flexed through 240 temperature cycles. And then your habitat pressure monitoring shows something you don't want to see. Not an alarm. If it had triggered an alarm, you'd already know where to look. It's a trend. Pressure is dropping, slowly, at a rate too gradual to trigger any automated warning. But the trend data doesn't lie. Somewhere in the walls there is a pinhole, probably a micrometeorite impact, the kind that would have burned up harmlessly in Earth's thick atmosphere, but punched clean through on Mars, where almost nothing burns up before hitting the surface. The hole is smaller than the width of a pencil lid. You can't hear air escaping. You can't feel the draft. At the current leak rate, you have about 90 days of breathable air left before pressure drops below survivable levels. Here's the gut punch. You cannot call for rescue. The idea of calling for rescue is something your brain reaches for automatically because it works on Earth. On Mars, it doesn't work. A rescue mission would take 9 months to reach you. You have 90 days. There is no rescue option. There is only finding the hole yourself, sealing it yourself, and surviving on your own, which is not a value or a philosophy, it's a literal requirement of the physics of distance. Your choices are: spend those 90 days methodically searching every square meter of habitat wall, knowing you might not find it in time, or accept that you will not find it and figure out what else you can do with 90 days of breathable air. There is no third option. There is no cavalry. That is the real answer to the question. Surviving the first year on Mars isn't about radiation or a catastrophic explosion or a suit rupture in the open air. The most likely thing to kill the first Mars crew is the slow, boring, compounding accumulation of small problems. Dust cutting power by 5% per month, food nutrition drifting downward, equipment seals degrading through the daily temperature grind, and a crew that's been isolated for 9 months in transit and is now isolated for 900 more days on the surface. Every system runs down, every margin narrows, and somewhere between day 1 and day 365, the margins on oxygen, power, food, and pressure all arrive at their worst point simultaneously. Not because of bad luck, because they all started degrading on the same day at roughly the same rate, driven by the same dust, the same temperature swings, and the same merciless distance from anyone who could help. The danger was never the monster under the bed. It was the slow leak nobody found yet.